Hello everyone, welcome in this lecture where we study on the equations reducible to linear differential equations with constant coefficient, where type 1 is Cauchy's or Euler's homogeneous linear differential equation. Now see, what is the general form of Cauchy's or Euler's homogeneous linear differential equation? It is of the form a naught x raised to n d raised to n y upon dx raised to n plus a1 x raised to n minus 1 nth order derivative with respect of y with respect to x plus and so on an minus 1 x dy by dx plus an y equal to f of x. What is the actually characteristic of this equation? You can observe that when we are having nth order derivative term, it is having multiplier x raised to n. For dy by dx term, we should have multiplier as a x. Okay, and once you identify that given equation is Cauchy's or Euler's homogeneous linear differential equation, we try to solve it, and this is a method of the solution. Here we have to put x equals to e raised to z, or when I take the log on the both side, we have log x equals to z. With this substitution, your first order derivative term x into dy by dx turns to dy, and x square d square y by dx square turns to d into d minus 1 operating on y, and so on, where this d stands for derivative with respect to z. Once you substitute all this in the given equation, then it reduces to linear differential equation with constant coefficient in variables y and z, which can be solved by using usual method, that is writing complementary function and particular integral. And once you got the general solution, in that general solution, finally you have to replace z by log x and e raised to z by x to get the solution of the given Cauchy's or Euler's homogeneous linear differential equation. Now look at the example. To reduce this linear differential equation, x square d square y by dx square minus 4 dy by dx plus 6y equal to x raised to 4 to linear differential equation with constant coefficient. What is the substitution? When we observe this given differential equation, you can see here the second order derivative has multiplier x square, first order derivative has a multiplier x. Therefore, it is Cauchy's or Euler's homogeneous linear differential equation, and therefore standard substitution to convert it into LDE is what? X equals to e raised to z. Therefore, correct option is B option. Now look at the second example. On putting x equal to e raised to z using d equals to d by dz, the differential equation x square d square y by dx square plus x dy by dx plus y equal to x is transformed into one of the following four forms, right? Now look at the solution. As we observed, the given differential equation is Cauchy's or Euler's homogeneous linear differential equation. We have to put x equals to e raised to z and x dy by dx equal to dy, x square d square y by dx square equals to d minus 1 operating on y, where d equals to d by dz. Okay, now using all these things in a given differential equation, we have d into d minus 1 operating on y plus the second term will be what? dy plus y equal to x equals to e raised to z. Therefore, on the right side, we have e raised to z. From each of the term on the left side, we can take y common, right? When I multiply this d inside the bracket, we get d square minus d. The second term becomes d, and from the last term, when I take y common, we have 1 here. Here plus d minus d get cancelled, and we have d square plus 1 operating on y equal to e raised to z. And this is your required option. Therefore, correct option is B option. Right, now see the third example. Here the given differential equation is x cube d square y by dx square plus x square dy by dx minus xy is equal to x raised to 4 upon 1 plus x square. On putting x equal to e raised to z, this equation transform into one of the given provided four options. Okay, now when I observe this given differential equation, it is actually not in Cauchy's or Euler's homogeneous form, because here for this this second order derivative term we should have x square. For first order derivative we have coefficient equals to x, and so on. Therefore, what should we do first? We should divide both sides by x, right, to convert it into the our required form. Therefore, dividing both sides of the given equation by x, we get this equation, that is x square d square y by dx square plus x dy by dx minus y equal to x cube upon 1 plus x square. Now it is Cauchy's or Euler's homogeneous linear differential equation. Now we have to substitute x equals to e raised to z, x dy by dx equal to dy, x square d square y by dx square becomes d minus 1 operating on, where d equals to d by dz, right? Using all these in the given Cauchy-Euler's homogeneous differential equation, we have d into d minus 1 operating on y plus dy minus y equal to e raised to 3z upon 1 plus e raised to 2z. Okay, once again taking y common from the left side, we have d square minus d plus d minus 1 operating on y equal to this term. Here plus d minus d cancel and we get differential equation d square minus 1 operating on y equal to e raised to 3z upon 1 plus e raised to 2z. Therefore, correct option is C option. Now see the next example. For the differential equation d square y by dx square plus 1 upon x dy by dx equal to a plus b log x, complementary function equal to question mark. These four options are provided. Now see, once again, this is not in standard form. Here again we have to multiply both sides by x square, right? Therefore, multiplying both sides of the given differential equation by x square, we have this x square d square y by dx square plus x dy by dx equal to x square into a plus b log x. Now it is in Cauchy's or Euler's homogeneous form, right? Here we have to substitute x equal to e raised to z and log x equal to z with x dy by dx equal to dy and x square d square y by dx square equal to d minus 1 operating on y, where this d equals to what? D by dz, right? Using this in the equation number 1, we get this first term equal to d minus 1 operating on y. The second term becomes dy, and as it is x square, here you know x equal to e raised to z. When I take the square on the both side, we get the value of x square equal to e raised to 2z. Therefore, in the right side, we have e raised to 2z into a plus b times log x. Log x equal to how much? It is equals to z. Therefore, just simplifying this linear differential equation in variables y and z, we have d square operating on y equal to e raised to 2z into a plus bz, right? Now, in this example, they asked to find out the value of the complementary function. Therefore, we should consider the auxiliary equation. Consider here a d square equal to 0 as an auxiliary equation. This gives us d equal to 0, 0. Therefore, roots are real and repeated. And therefore, by considering case number 2 for writing the complementary function, we can write down the yc is equal to c1z plus c2 e raised to 0z. But you know e raised to 0z is 1. Therefore, yc is equal to c1z plus c2. Now, just by replacing the value of a z in terms of x, we have required complementary function equal to c1 into log x plus c2, because z equals to log x for this equation. Therefore, correct option is a C option. Now, see in the example number 5, we have differential equation in variables u and r. The given differential equation is what? R square d square u by dr square plus r du by dr minus u equal to minus k into r cube. Okay. Now, to find out the complementary function, we have these four options with us. One of them is correct. And now let us look at the solution. Given differential equation is Cauchy's or Euler's homogeneous linear differential equation, because here second order derivative has a multiplier r square, first order derivative has a multiplier r, and so on. Therefore, this is Cauchy's or Euler's homogeneous linear differential equation. Therefore, we should substitute that independent variable, that is r equal to e raised to z. Therefore, r into du by dr equals to du. R square d square u by dr square become d minus 1 operating on u, and so on. And using it in the given Cauchy's or Euler's homogeneous differential equation, we have d minus 1 operating on u plus du equal minus u equal to minus k r cube term. This r equals to what? E raised to z. When we take the cube on the both sides, this r cube become what? E raised to 3z. Therefore, here we get minus k e raised to 3z. Right? Now you can see here plus and minus get cancel, and your auxiliary equation is what? D square minus 1 equal to 0. And this gives us d equal to plus and minus 1. Therefore, roots are real and distinct. By using case number 1 of complementary function, we can write down uc equal to, that is complementary function corresponding to dependent variable u equal to c1 e raised to 1z plus c2 e raised to minus 1z. Okay, and just by replacing this e raised to z equals by r, we get required complementary function in terms of r is what? C1 r plus C2 This e raised to minus z becomes r raised to minus 1 because here I raised both of the powers by minus 1 and this e raised to minus z become r raised to minus 1. Therefore, we have this r raised to minus 1 becomes what? 1 upon r, and therefore correct option is B option. Now look at this next example to find out the particular integral for the given differential equation. Okay, here again, you know, this is a Cauchy and Euler's homogeneous differential equation. Why? Because the second order derivative has a multiplier x square, first order derivative has a multiplier x, right? Now look at the solution. Here again, we have to put x equal to e raised to z, x dy by dx equal to dy, x square d square y by dx square become d minus 1 operating on y. Using this into the given Cauchy's or Euler's homogeneous differential equation, we have d into d minus 1 operating on y. The second term becomes this minus 4 kept as it is, x into dy by dx become dy plus 6y equal to, on the right side we have x raised to 5, but we know x equal to e raised to z. Raising the power by 5, we have x raised to 5 equal to e raised to 5z. Therefore, on the right side, we have e raised to 5z. Now, just by taking y common and simplifying the terms of d, we get the polynomial d square minus 5d plus 6 operating on y equal to e raised to 5z. Right? Here, they ask to find out the particular integral only. Don't try to find out the complementary function to waste the time. Only concentrate on the particular integral. Let yp is equal to 1 upon d square minus 5 plus 6 operating on e raised to 5z. By using shortcut method for the exponential function, we have to replace d by a. A is equal to how much here? It is equals to 5. Therefore, replace d by 5. Here we get in the denominator 1 upon 5 square, that is equal to 25, minus 5 5 is 25 plus 6, right? 25 cancel, and we get yp equal to e raised to 5z upon 6. Again, replacing this e raised to z by x, we get yp equal to x raised to 5 upon 6. Therefore, correct option is A option. Now, in the next example, they asked to find out the solution of the differential equation x d square y by dx square plus dy by dx equal to x. They asked to find out the solution. It means that here we have to find out the complementary function as well as particular integral, and hence ultimately general solution. These 4 options are provided. Now, as we observe, it is what? When I multiply both sides by x, it reduces to the Cauchy's or Euler's homogeneous differential equation. Therefore, what is your first step? Multiplying both sides of the given equation by x. We get this kind of equation. Okay, this is now in the standard form of Cauchy's or Euler's homogeneous linear differential equation, where we have to put x equals to e raised to z, and therefore x into dy by dx equal to dy, and x square d square y by dx square become d minus 1 operating on y. Okay, using this substitution in this form, we have this differential equation d square y equal to e raised to 2z, right? Now, in order to find out the complementary function, consider the auxiliary equation, that is d square equal to 0. This gives us d equal to 0, 0. These roots are real and repeated roots, and therefore your complementary function is what? C1z plus C2 e raised to 0z, where e raised to 0z is 1, and therefore final complementary function is C1z plus C2. Now again, I would like to find out a particular integral also. Now see how to find out a particular integral. By definition of particular integral, we have yp is equal to 1 upon d square operating on e raised to 2x. Here, according to the exponential rule, we should replace d by 2. Using shortcut method, when I replace d by 2, we have 2 square is 4 in the denominator, and therefore particular integral is what? E raised to 2z upon 4. Now, taking the addition of the complementary function and particular integral, we get general solution as y equal to c1z plus c2 plus e raised to 2z upon 4, right? But in order to obtain the solution in terms of y and x, we can replace this z term, that is e raised to z by x and z by log x. You can see here we get y equal to c1 into log x, replacing z by log x plus c2 as it is, plus, as you know, x equal to e raised to z, just by squaring both sides, you can write down the value of e raised to 2z as x square. Therefore, the last term is what? X square by 4. Therefore, correct option is D option. Thank you. Thank you for watching.